Hey everybody, Dr. A here, and in this video we are going to be discussing heaving in soil downstream of a sheet pile wall. So let's go ahead and get started. It turns out that we can use the concept of seepage force, which we talked about in a previous video, per unit volume to check for heave potential on the downstream side of a sheet pile wall. Okay, now the way we can do this is based on some theory that Terzaghi developed in 1922. So what he determined is that for a sheet pile wall, soil heave could potentially occur within a horizontal distance of d over 2, this is d over 2, from the downstream side of the wall. Okay, so let me draw a picture of what that would look like. Let's say that we have the water level here, okay? And let's say that we have a sheet pile wall. Let me draw that a little bit better. Let's say that we have a sheet pile wall here, okay? And on the downstream side, let's say that the water level is maybe a little bit lower here, okay? And let's say that we have the ground surface, say, about right here. Okay, there's the ground surface. And let's say that, you know, this ground surface is some kind of thickness. Maybe we'll call this thickness capital H, okay? And so all of this is permeable material here. So we'll make a note here. We're going to say permeable material. And then below this line, this is impermeable material here. Okay, so the water is going to tend to seep from the upstream side to the downstream side. And, you know, you could model that aspect from a flow net. So let's say that this water height here, we'll call it maybe little h1, and then on the downstream side, we can call this little h2, okay? And of course, as we already mentioned, this is the sheet pile wall, all right? Now, what is this d over 2? We're saying that heave could occur at a distance of d over 2. Well, d is going to be the depth of embedment of the sheet pile wall. So I'll make a note over here on the side here. I'm going to say d is the depth of embedment of the sheet pile wall. So when we say that heaving could potentially occur within a distance of d over 2 on the downstream side of the sheet pile wall, what we're saying is, let's change colors here. What we're saying is, if you project a horizontal distance on the downstream side of the sheet pile wall, this distance will be equal to d over 2, and then we can project it up, and this shaded area is what we would call the heave zone, okay? Heave zone. And if you remember from some previous knowledge, what does heave mean? Well, if you have a type of soil, usually it's a soil with a lot of fines like silts and clays, heave is a term that means loss of stability, okay? So that means your soil in this heave zone will lose stability, and you could have blowout here. As water is seeping around here, you can have blowout in this vicinity, okay? So that's what we mean by that. Now, what we can do, or what we need to do, is then explore a factor of safety against heaving, all right? So the factor of safety against heave in this situation is Fs equals W prime over U, okay? Now, what is W prime and what is U here? Well, W prime is going to be the effective weight of soil in the heave zone, And this is going to be in terms of per unit length of sheet pile. And then U is going to be the uplift force due to upward seepage in the heave zone. All right. So let's maybe look at this more carefully. I'm going to peel this out. I'm going to look at this heave zone, and I'm going to kind of blow it up and look at a free body diagram of the heave zone. So let's change colors and let's investigate this. FBD of heave zone. All right. So if I kind of expand this out, here's my heave zone kind of blown up. All right. And the vertical dimension of the heave zone is that depth of embedment D. And of course, the width or the horizontal dimension of the heave zone is D over 2, okay? And so what we will end up having is the effective weight of that little element, and then we're going to have the uplift force U here, okay? So if this looks familiar to you, it should. This is a similar kind of diagram that we've explored in another video when we talk about seepage force per unit volume, okay? And so let's first start with looking at the effective weight here, all right? So what is this effective weight going to be? Well, it's quite simple. It's W prime is going to be 1/2 D squared gamma prime. Now, I didn't just make that up, okay? Where does this come from? Well, again, it's going to be equal to D, which is this dimension, times D over 2, which is this dimension, right? And then times gamma prime, all right? Now, you might be thinking, well, wait a second, this is just an area times gamma prime, right? It's this area here, all right? Well, this is still kind of the same idea as seepage force per unit volume, except you are looking at this per unit length of sheet pile wall, okay? So this W right here is coming in and out of the screen at you. This is on a per unit length basis, okay? So that's why it's not specifically divided by volume, and that's why we don't have volume times unit weight, effective unit weight. So we're going to say this effective unit weight has units of what? Well, it's going to have units of force per unit length, right? Because you've got an area here and you've got multiplied by force per unit volume here because this is a unit weight. So you're left with force per unit length, okay? So that's W prime. And again, we normally see this version of the W prime formula. Now, what about U? What about the uplift force? Okay, well, similar idea. We're going to say the uplift force is going to be equal to, it is a volume times an average hydraulic gradient times the unit weight of water, okay? Now, again, what is this? How is this volume going to be represented? Well, it's not really a volume because we're basing this on a per unit length, right? So the way we would express this is still, D, let me put an equal sign, D times D over 2 times I average times the unit weight of water, all right? And so, again, this can be, packaged a little bit more nicely as 1/2 D squared I average gamma water, all right? Now, what is I average? Well, I average is the average hydraulic gradient in the heave zone, okay? So it's the average hydraulic gradient through that distance D, all right? So if we piece all of this together, you know, again, we had this factor of safety. Let's scroll back up. We had this factor of safety here, W prime over U. So if we piece this together, Fs equals W prime over U. All right, how does this all substitute together? Well, again, it's going to be, you know, 0.5 or 1/2 d squared gamma prime, all divided by 0.5 d squared I average gamma water. All right, so we see some things cancel here, and we're left with this term gamma prime over I average gamma water. Okay, now how do we dig into, no pun intended, how do we dig into I average a little bit more? Well, remember, we're looking at the average hydraulic gradient through that block of soil. So I average is going to be taken as 1/2 times little h1 minus little h2 divided by the depth of the block. Okay, so again, it's the head at the top of the block and then the head at the bottom of the block on average, and then divided by the flow length, right? So the flow length that we're considering is that depth D right here. And why is that? Well, again, we're flowing in this direction, right? So when you flow in that direction, the flow length that you're interested in for the heave zone is D. So that's why that D is in the denominator here for the average hydraulic gradient. All right. And so you can substitute this term into this denominator. And what happens when we do that? Well, some things rearrange a little bit, and we can get factor of safety equals D gamma prime over 0.5 gamma water times H1 minus H2 there. Okay, and so we have this kind of factor of safety term here that we can use. Now, there's been some other researchers that came after Terzaghi that kind of furthered this field of study, and they came up with some different coefficient terms that can be substituted in to this denominator here. So I'm going to make a little note here, and I'm not really going to get into it in this video, but we're going to say other researchers have concluded that the coefficient of 0.5 in the denominator, and again that's this 0.5 right here, may be too high and may vary between approximately 0.27 up to about 0.37, depending on the total thickness of the permeable layer, which we defined earlier as capital H in our figure, our original figure here, capital H. Okay, so again, I'm not going to get into exactly what what these other researchers kind of came across, but it has been further developed since then. So for the purposes of some theoretical background, you would use this version of the factor of safety that we just kind of derived. But depending on your particular source that you're citing, or depending on the specific field situation, it might be worth looking into the further development of this after Terzagh's time and see if this coefficient of 0.5 is really the most appropriate thing to be used in a field situation, or based on what a problem may ask you by a professor, and you might conclude that you need to extract a different coefficient here instead of 0.5. You might find that it should be a little bit lower than that depending on the total thickness of the permeable layer. So one of the, just as a reference for you, one of the sources that you can look into, let's write this as a additional source to look into this, would be from Tanaka and Varut. Make sure I spell the names correctly. And that was from 1999, if you want to look into an additional source for the development of this coefficient here. So that concludes this video on this background information. If you found this helpful, please hit like and subscribe. Thank you for watching.